that is kind of similar in nature, but with a little bit of a difference. All right, so let's double check. It is recording, and we can now go to the homework assignment. So this is cisp310, and we are talking about treasure 1. Treasure 1 is here, and treasure 2 is already up. So during lab time for today, we have something to do in the lab. So let's take a look at treasure 1 first. We'll go ahead and finish the solution of treasure 1 first. So I'm going to download it. This is like the third time I downloaded it. That's why it has a suffix of 2 in parentheses. And we'll go ahead and see if I already have the folder. Yep, I do. All right. So just looking at the source code first. This is the exact source code that you have to start with. The bottom line is, by the time we get to this label, stop here, register EBX, which is a 32-bit register, should have a content of this number, and it is explicitly in base 10. Okay, so we know the value in base 10 looks like this. It's not going to be very helpful when it is in base 10, because as a base 10 number, it's you cannot really see the byte boundaries when it's in base 10. So you want to convert it into some kind of base 2 or base 16 number in order to find out, okay, I need to know what goes into the least significant A bits, the next A bits, the next A bit, and the next A bit. So that's the first thing you need to do, is to take this number and then change it. What I'll do here is I'm going to start up another terminal, so this way I can use one terminal to look at the code and use the other one to go into GDB, just to run GDB for various purposes here. So the first thing I want to do is to convert this number into hexadecimal, because that's the easiest way to look at, okay, this is a number, but how is it represented in 4 bytes, okay? Because we want to find out what those bytes are. Okay. So we'll go to the same folder here, and I'm just writing GDB without anything, because GDB all by itself can be used like this. So the first thing we need to do is to print /x or /z, because that gives us all the leading zeros, if there are any. And we just need to copy this number and paste it over here. And that number turns out to be in hexadecimal to be 2E, 4 zeros, and then followed by 2E. So we are looking for this particular pattern in EBX after all the instructions are done. Okay? So the way to do this homework assignment is to kind of work like a detective. So you start with a crime scene, and then you work your way back to find out what happened, okay, or what you can do to make this happen. So the last instruction is this one here. So the clue to this one is, okay, what do we need to put into BL in order for EBX to end up with 2E as the least significant byte? Well, this is BL. BL is bit 0 to bit 7 of EBX. So this 2E is what we need. There are actually 2 bytes of 2E that we can load into BL. Because when you look at how memory is initialized, which is all the way at the beginning here, we got, okay, I take it back, we got 3 2E's. We have 1 2E here, 1 2E over here, and 1 2E over here. So any one of those 3 2E's would do it, okay? So you have to kind of ask yourself, okay, so now I know we need to load one of these 2E's into BL, which also means EAX should have the address of one of those 3. Now, which one of those 3, I'm not sure at this point. Okay, maybe there are different solutions to this particular problem, but I need to look into it and find out, okay, how can we get one of those addresses into EAX by the time we get to the move B EAX to BL instruction. Is that part okay? Okay. So now is a good time to look into how memory is laid out here, and really just label each location with its own address in the form of L1 plus something or L1 minus something. So this is a good time to, you can use a spreadsheet, you can use a text editor, you can use a piece of paper There are many ways to do this. So, just for convenience, I'm going to use a spreadsheet just because, it is one of the easiest way to make a table in a class like this. So I'm just going to make a really simple table here. And the table is going to correspond to our source code. And all I want to do is to lay out every single byte in memory in the .data section, just so that it's easy for me to refer to, oh, okay, we are now referring to this location or this location and whatnot. The .byte construct, or the .byte, I shouldn't say construct, but the .byte directive is asking the assembler to allocate 1 byte and initialize it to the value of 2e in hexadecimal. And 2e is already a byte, so we'll just go ahead and say, okay, the first byte is 2e. The next construct is a .word. A .word is asking the assembler to allocate 16 bits or 2 bytes in order to represent whatever value that we wanted to represent. In this case, the value is 67 in hexadecimal, which only needs 1 byte to represent, but it will allocate 2 bytes anyway. So that means it's going to allocate 16 bits. The most significant 8 bits will be zeros. They will be leading zeros. Now, with a multi-byte integer, endianness comes into play because you have to figure out, okay, do we store the most significant byte at the lowest address, or do we store the least significant byte at the lowest address? Which one should we use? The least significant byte, because the i386 is a little endian processor, which means the least significant byte is at the lowest address. So in this case, 67. Maybe I should just use it. Just make it explicit, these are all hexadecimal numbers. So 0x67 is the next byte, and then 0x00 is the next one, because that's the most significant byte of the 16-bit integer. And then we now have the .int, which is telling the assembler to allocate 4 bytes to represent what is following here. This one actually is somewhat straightforward because I'm using all 32 bits here. So we'll have a 2e first, and then we have a 67, and then we have a 5f, and then another 2e. And then we have 4 bytes, which is corresponding to this particular .int here. Those 4 bytes, I have really no idea what the exact value is. I mean, you can find it out in GDB, but looking at the source code, there's no really easy way to find out. So what I'll do is I'm combining these 4 bytes into one single cell and say, oh, it is just L1 minus 6. Whatever that value is, I'm using these 4 bytes to store it. And that goes for the next 4 bytes as well. I'm combining those 4 locations and say, okay, whatever it is, it's just storing the value of L1 minus 7. I intentionally do not use column A for a reason. Column A is going to indicate the label. L1 is right here. In other words, the label L1 is basically the address of the least significant byte of the .int L1 minus 6 line. The address is always only of a byte, not the address of a word or a long word, because the i386 is a byte addressable architecture. So whenever we refer to a byte, excuse me, take it back. Whenever we refer to an address, it is always the address of a byte. Now in this case, this turns out to be the beginning of the entire L1 minus 6, which is taking up 4 bytes. But nonetheless, L1 is the address of a single byte, which means the next location is also known as L1 plus 1, L1 plus 2, this is L1 plus 3. So L1 plus 4 is here. It is the first or the least significant byte of the 4 bytes that store the value of L1 minus 7. So this is L1 plus 5, L1 plus 6, and this is L1 plus 7. The offset also goes in negative, so if you're looking at the byte right before the .int L1 minus 6 line, this is L1 minus 1, L1 minus 2, L1 minus 3, L1 minus 4, L1 minus 5, L1 minus 6, and here's L1 minus 7. Okay? Are we doing okay so far with how memory is laid out? Okay. So now that we are looking at exactly all the bytes that are initialized in the data section, and have quote unquote a label next to it in terms of L1 plus something or L1 minus something, then it's easier for us to look at the solution, what we need, and then figure out how we can get to it. So let me put this one on the side, and I think I can do it. I just have to use the keyboard and not use the mouse, so I can actually scroll around here. Okay, we want this BL to have the content of 2E, and we have found 3 2E's here. So we got 1 2E here, 1 2E here, and 1 2E here. It is possible that we have multiple solutions. I don't know yet, okay? But in order for one of these 2E's to end up as BL, we need EAX to have the address of one of these 3. In other words, EAX should have L1 minus 1, L1 minus 4, or L1 minus 7. Okay? That will make it work. But the question is, EAX itself is also getting its own content from some address, which is, in this case, EAX is an indirect operand to put back into EAX. So that means, L1 minus 7, L1 minus 4, or L1 minus 1 has to be stored somewhere in memory. And you can see right here, stored in memory is only L1 minus 6 and L1 minus 7. So that leaves us no choice but to say that L1 minus 7 has got to be the value in EAX when we load indirect EAX into BL. So the previous instruction, which is this instruction here, in order for EAX to end up with L1 minus 7, I have to load those 4 bytes from the location L1 plus 4, because L1 plus 4 is the least significant byte, which is also the first byte of those 4 bytes representing L1 minus 7. So that means before that, with the previous instruction, EAX should have L1 plus 4. So that means this question mark here should be L1 plus 4, immediate. Is that okay or not? The key concept here is, do we know which part talks about the address and which part talks about the content in EAX? When you use indirect mode, which means we're putting parentheses around EAX, we are treating the value of EAX as an address. We go to that location, retrieve 1, 2, or 4 bytes out of that location, and put it into that becomes the value that we are moving. Yep.
With that in mind, isn't it a little bit redundant to have the EAX in parentheses and assign the value of EAX in parentheses to the storage of EAX?
Okay, let me turn on the line number so it's easier to refer to which line. Okay, there we go.
Number 23.
Number 23.
You're taking the value stored in EAX and storing it as the value of EAX.
No. This one, okay, the first operand, okay, let me just move the cursor so we know which one we are talking about here. Okay, we're looking at this particular operand here. As an entire operand, the first operand is an indirect operand, which means I am not moving from EAX to EAX. The first operand is indirect. It is not a register operand. It is an indirect operand, which means I'm using the value of EAX at that point in time as an address.
Okay.
I use it as an address. I go to that particular memory location, and I grab, in this case, 4 bytes from that location, starting with that location, and copy those 4 bytes to EAX again. So I'm overwriting EAX.
Okay, so the storage of EAX before that is the address of L1 plus 4, correct?
That is correct.
Okay, that makes sense.
Now, L1 plus 4, from the perspective of line 22, it is just computing the expression L1 plus 4 and copy the 4-byte representation of that value to EAX. So at that point, on line 22, we don't even know whether EAX should be interpreted as an address or not. It's just an integer. It's just like a 4-byte of bit patterns.
Okay.
But by the time we get to line 23, the first operand says, okay, now treat EAX as an address, as a pointer.
For the storage of EAX.
EAX is a register. It does not have a storage. It is not in memory.
Okay.
But EAX serves as a pointer to go to 4 memory locations in this case, so that the first operand is actually specifying the value of those 4 bytes in memory that EAX is pointing to.
Okay.
And then we use those 4 bytes to overwrite EAX itself. So the destination operand, which is the second operand, EAX, is a register operand. We are overwriting the value of EAX itself.
Okay.
So after line 23, EAX will have L1 plus 7 because L1 minus 7 because L1 minus 7 is the value stored from L1 plus 4 to L1 plus 7 in memory. So by the time we get to line 24, EAX has a value of L1 minus 7, and we use the indirect operand, which means we go to the location of L1 minus 7 to retrieve that one single byte because it's a move byte instruction and move that into BL. Yep, go ahead.
So line 24, you only move 1 byte?
Yes, because it's a move byte instruction. There are 2 clues that it's moving only 1 byte. Move B, the B indicates it's a move byte instruction. Then BL itself is also an 8-bit register, so we have to be moving only 1 byte.
As well as BX?
BX is 16-bit, and then EBX is 32-bit. All right, so are there any questions about this one? I mean, once you know how to get to this one, the other ones are pretty much the same. Any questions about Treasure 1? No questions? All right. Yeah, this one really just kind of exercises a few key concepts, which is what is a register operand, what is an indirect operand, and what is an immediate operand. Those are the only 3 concepts used here. The move instruction is just a copy instruction. It takes whatever the first operand is and copy it to the second operand. That's all it does. There's no actual computation in this case. If there are no questions about this, I'll still leave this one on the screen just in case we want to get back to this one. And then we're going to move forward to talk about Treasure 2, which is your next homework assignment. Treasure 2 is a little bit like Treasure 1. It's not identical, but it's pretty close with one little twist. Okay, so we'll go ahead and download treasure2.tar.gz. It has almost exactly the same structure as the other homework assignment, and I'm going to use this tab here to take a look at that one. So once again, tar xcvf treasure2.tar.gz. Go to treasure2, and it has treasure2.s. And it's almost exactly the same. In fact, I was so lazy, I kept using the same thing as the beginning of the entire thing. The only difference is here. The value of EBX after the entire sequence of instructions is supposed to be this number, and this time you already know that you have to convert it into hexadecimal first to look for the byte patterns. The instructions are also slightly different. If you look at the instructions, the first one is kind of the same as the, nope, I take it back, it's not the same, because this one does not have the, okay, let me show you what it was before. With Treasure 1, it looks like this. It has 2 indirect, consecutive, to each other, and this one has 4 instructions. So it has a move instruction into EAX, and it has a move indirect into EAX. And then I throw something that is kind of new to us into this whole thing. I'm adding something to EAX. So you have to figure out what I'm adding to EAX here. Now, the only type of operand you can use is are immediate operands. So that kind of limits what you can really do with this one, what you can add to EAX. And then the next one, the last one, is going to move something into EBX. This is the only chance you can put something into the most significant 16 bits of EAX, because you cannot address the most significant 16 bits of EAX with any other name. So that's a good clue of what you need to do for those two question marks. The next three instructions are also different. Okay, this is treasure 2. And in treasure 1, it looks like this. Okay, in treasure 1, we have moving something into EAX and then indirect into EAX, indirect from EAX to BX. With treasure 2, it looks like this. Oops, take it back. So we move something into EAX, we add something to EAX, and then we move WEAX, to BX. So with this one, there are possibly many solutions. Okay, so you just have to figure out one way to make it work. Are there any questions about this part? In a way, this is actually easier if you know what I'm asking, and if you know the instructions and the addressing modes. This is actually a whole lot easier, because you can always say, oh, okay, I can just turn this into a very special case and basically just forget that there's an add instruction here. I'm not going to tell you, what you can do to kind of think in that direction. The last instruction, which is the one that will override the least significant 8 bits of EBX, is just 2 instructions. Okay, you put something into EAX, and then you immediately use EAX as a indirect register and use it as a pointer to copy a byte into BL. So in a way, it is easier than the first homework assignment. But you do have to kind of think in a flexible way, and not think in the way of the first homework assignment anymore, and just kind of look at each situation differently and try to figure out the answer to that part. So are there any questions about this homework assignment? Yep.
The add-L instruction.
The add-L instruction is an add instruction. It adds the first operand to the second operand, and it stores the result in the second operand. We kind of touched on that in the previous class too. All right, so that's your second homework assignment, in your treasure 2 as homework assignment. Yep.
You said the data values or whatever were the same, the values that you used from the last one?
The data value?
I'm just saying the wrong word, but
Once you
like
add up the
or
EBX?
5 are the same values, and BL one's the same value as well.
Yeah, I didn't change how the memory content is initialized. So when you look at how the memory is initialized, it's exactly the same as last time.
Okay.
So I have just done like one part of your homework assignment, because the spreadsheet that I was using, not this one, close the one that we don't need, and not this one. This one here. So I have already done, some portion of your homework assignment, because the layout of memory is identical to treasure 1. How many people somehow ended up with a representation like that, either on a piece of paper or, okay. So that's basically what you need to look at in order to understand, oh, okay, we need to copy this byte to here, but how do I get to that part? Any other questions about the homework assignments? Treasure 1 or treasure 2? Is everybody kind of relating what you learned from pointers in C++ to what we're doing here? They're very much related. Right. If there are no questions about this, then we'll move on and talk about, we'll finish up the add instruction discussion, and then we'll move on to subtraction and comparison, which is, actually not very exciting, but they're very useful. So we'll go ahead and start with arithmetic operations. This one is really old, kind of an older content that I have written a long time ago. It's still relevant, it still applies. Some of these topics we have already talked about already. So we talked about addition, I don't think we have to talk about this again because we have already done it many, many times. The add instruction is discussed. I'm trying to look for where I talk about the add instruction. It's just addition in terms of concept. The add instruction is probably, there are several places where I talk about the add instruction. Just have to find one that works. Interesting, that didn't work. There we go. So we talked about the add instruction in topic 1, or just binary addition. And let's take a look at this one. Yep. All right. So this is the one that we talked about. We used this slide to talk about the add instruction itself, and last time I commented on how short this particular page is, because for the most part, the add instruction is just like the move or copy instruction. Except in this case, instead of copying the first operand to the second operand, you are adding the two operands first, and then the sum is stored in the second operand, which is always the destination operand. Is that okay so far? Okay. So that's what we talked about last time. And you can use the same kind of operands that we have talked about so far. The first operand being the source operand, kind of read-only operand, can be immediate, can be register, can be indirect. The second operand can only be register or indirect because you can not store into an immediate operand. You can store into a register, you can store into a memory content or memory location, but you cannot store into an immediate operand. So that's the only thing that you have to remember is it's just kind of like move, except you're adding and then you're storing the sum into the second operand. All right, so are there any questions about the add instruction? The suffix of the add instruction is the same as the move instruction. In other words, if you don't specify something here, the assembler will pick for you. And so most of the time it will pick something that is correct, but you want to kind of specify all the time so it is not possible for the assembler to make an assumption that is not what you intend. So once again, this letter here can be B for byte, W for word, which is 16-bit, and L for long, which is 32-bit. So are there any questions about the add instruction, how to make use of it? No questions about that? Okay, yep, go ahead.
Now, if I have a 32-bit number in the register and I added 8 bits, would it?
You cannot do it. You cannot mix it.
Okay.
So if you specify an add long instruction, both operands will have to be 32-bit operands. If you specify one to be 32-bit and the other one to be 8-bit, the assembler will complain about it.
Okay.
Yep. All right. Any other questions? If there are no other questions, we'll move on and talk about subtraction. Okay, very exciting topic here, comparing and subtracting. So comparing and subtracting is, well, I was just kidding when I said it was very exciting. It's actually not very exciting. So binary subtraction. Okay, we talked about all of this stuff already, so we'll just kind of quickly go over all this stuff here. In binary subtraction, 0 minus 0 is 0. 1 minus 0 is 0. 0 minus 1 is a 1 with a borrow. All the other cases do not have a borrow or a borrow of 0. And the 1 minus 1 has a borrow of 1 minus 1 is 0 with no borrow. So those are the only 4 rules for binary subtraction, which is a whole lot better than in decimal, because in decimal you have to remember 2 minus 7 is 5 with a borrow. Okay, there are a lot more cases to memorize than in binary. So after the rules, come the equations. So the equations is kind of the same as addition. In other words, the result has the same equation as for addition. The only part that is different is the borrow bit is a little bit different. It has to take the negation of x first before we use a conjunction to combine it with y, which is the other bit that we are adding. We did this already in the logic sim exercise to convert like a half adder into a half subtractor, and we talked about how we just need one extra NOT gate to turn a half adder into a half subtractor. But the way we structure half subtractors into full subtractors is exactly the same as what we do with an adder. So that's the only difference here. So we basically we went over this part already. Combinatorial multi-bit subtractor basically it's the same thing as with an adder, with the construct of a full subtractor, and you just have basically if you're just stacking up half full subtractors, then you have a propagational delay that is proportional to the length or the width of the integer that you're dealing with, which is not acceptable for fast processors like the Intel processors. So what this means is a lot of times we will basically resolve the equations so that they become much more complicated than what we have to deal with in a half subtractor, but then the processor will be able to do subtraction faster than using just a stack of full subtractors. All right, so that's it's a reference back to the full adder concept. Basically the picture in the full adder concept also applies to subtracting with a half subtractor and full subtractors. So not too much new stuff here. The borrow from the most significant bit is kind of like the carry from the most significant bit for adding. It is not stored as a part of the result, but the processor does have one place to store that one bit, because in this case the borrow bit is actually very, very useful in a subtraction or a compare instruction, as opposed to the carry bit from an addition. All right, so we're moving on to subtraction and comparison. The subtraction instruction looks like this. Okay, instead of using add, ADD, we use sub, for subtraction. We have the same letter code to indicate the width of the operation: B for 8-bit, W for 16-bit, and L for 32-bit. And we have the first operand as the source operand, and the second operand as the destination operand. But with subtraction, you have to be careful. You have to be mindful of which one is being subtracted from which other one. Because with addition, it doesn't matter. It's commutative. But subtraction is not commutative. In this case, we are subtracting 32 from EAX, and then the difference is stored in EAX. So 32 as an immediate operand is still the source operand. EAX is still the destination operand to store the result of the subtraction. But the direction of the subtraction is we are subtracting the first operand from the second operand. And then we store it back into the second operand. Okay. Are there any questions about the subtraction instruction? Yep.
When you do that, is it subtracting in decimal or hexadecimal?
It doesn't matter. Subtraction is done, to the value,
That's right.
and in the processor, it's done in binary. Okay. Any other questions about this? So it also follows all the other same rules, which means the first operand can be immediate, but the second operand cannot be immediate. Any other questions about the subtraction instruction? After the subtraction instruction, I have one sentence to describe the compare instruction. Basically, the compare instruction uses CMP instead of SUB. It performs the same operation of subtracting, except it does not store the result into the second operand. That's all. Okay? It goes through the entire motion of subtracting the first operand from the second operand, just like the subtraction, except with a compare instruction, it does not store the result into the second operand. Is that okay so far? All right. So what we'll do next is we will go take a look at the 4 flags that we have talked about so far and see how they apply to subtraction. So we still have to talk about the carry, which is also known as the borrow flag. In terms of hardware, they are the same flag. So if you have an add instruction and then the subtraction instruction, the carry flag, quote unquote carry flag, will be overwritten by the subtraction instruction, and it's being used as the borrow flag. The 0 flag is the same, the sign flag is the same, and then the overflow flag is a little bit different, or it's defined a little bit differently. So, so what I'm going to do is I will make a copy of the logic sim file that we talked about last time. So let's take a look at the file names, CRRC. So last time we talked about, oh, yeah, I think I put it into text processor somewhere. Yep. Okay, so last time we talked about flags, which is a only for addition. So this time what we'll do is we'll also do it for subtraction. Okay. In fact, what I'm going to do is to copy flags to subtraction flags. So now it's a different file. I can zip up everything and upload it to Moodle at the end of the class so that you guys will have a copy of the simulator as well. So now we can go ahead and use, just java-jar downloads logic sim and give it subflags.circ. All right, so this is exactly the same thing as what we saw last time, which basically has, let me zoom in a little bit so this way you can see better. We have two input numbers. We have an adder here. The adder has an output. The output is split into 4 different lines to give us, the 0 flag, because we have to feed all 4 bits into a OR gate and then negate the output of the OR gate into the 0 flag. The carry flag out of the adder is all by itself known as the carry flag itself. The sign flag is the most significant bit of the result of the addition. And then the overflow flag is kind of the most complicated one, because the overflow flag will turn into a 1 if the sign of the sum does not make sense. Okay, if you look at the sign of the 2 numbers that you're adding, and then you look at the sign of the result of the sum of the addition, if the sign of the sum does not make sense, then the overflow flag is a 1. So that's what we talked about last time. Now we want to talk about subtraction and how subtraction is going to affect these 4 flags. Almost exactly the same way, except for one that is entirely different. So what I will do is I will take the adder out and go to arithmetic and put in the subtractor. Okay, so now we have a subtractor, and we have to turn the number of bits back down to 4 because otherwise it complains about it. So now we have a subtractor. Now with a subtractor, you have to remember which one is being subtracted from which one. So when you go to the first pin, it says this is the mean. This is the number from which to subtract, so that will make it the second operand in the subtract instruction. And this one is the number to subtract from the minuend. Is it minuend? Okay, so this is the first operand. Okay, so this is the second operand, this is the first operand. Okay, let's give it a try, right? So let's go to the simulation mode here, and we'll try 0, 0, 0, 0, 0, 0, 0, 1. Oops, 1. There we go. So it is subtracting 1 from 0 because the result is 1, 1, 1, 1 with a borrow in the end. Okay. Are we still doing okay so far with the result of the subtraction and also the quote-unquote carry flag, which is now the borrow flag? Is that still okay? The 0 flag is exactly the same as last time. We just take the output out of the subtractor, combine everything using a OR gate, and then negate it so that if the result is 0, the Z flag is a 1. If the result is non-zero, the Z flag is a 0. So it's still pretty much the same thing. So let's go ahead and try. Okay, let's specify 1 minus 1, and you can see the Z flag is a 1. Okay, makes sense because 1 minus 1 is 0. So if you feed all 4 zeros into an OR gate, the output of the OR gate is also a 0. When you negate a 0, it becomes a 1. So the 0 flag is a 1 in this case. Okay. The sign flag is also exactly the same. It is just tapping out of the most significant bit of the output of a subtractor, just like it's tapping out of the most significant bit out of an adder. So it is not changed. The carry flag is now our borrow flag, but other than that, it's not changed either. The overflow flag, on the other hand, is the one that doesn't make sense anymore. So we want to kind of come up with some examples to illustrate when is the overflow flag of a subtraction not making any sense. Okay, so we'll take a look at a few cases. And then we'll go back and change the logic here to reflect that. So we'll go to Accessories, start up my text editor, and now we'll go through a few examples. So let's go through a few examples where the sign of the result does make sense. Okay? So we'll start with, let's say, 3, and we want to subtract 5 from it, and the result is supposed to be -2 in base 10. So let's do this in 4-bit binary subtraction. 3 is 0011, 5 is 0101. So we perform a subtraction here. And this row is only for the borrow from the previous digit. So we're going to go through this calculation kind of the same way as we usually do. 1 minus 1 is a 0. 0 minus 0 is a 0. But because neither subtraction gives us a borrow, so that means the borrow from the next digit is a 0. 1 minus 0 is a 1. 1 minus 0 is a 1. And once again, neither gives me a borrow, so the borrow to from the next digit is also a 0. 0 minus 1 is a 1, but this time that gives us a borrow right away, so we put a 1 here. 1 minus 0 is a 1, so we put a 1 here. 0 minus 0 is a 0. 0 minus 1 is a 1 with an extra borrow. Okay? So from this subtraction, we can see that the borrow flag, which is also known as the carry flag, is a 1. We can see the result is non-zero, so the Z flag would be a 0. We can see the sign flag is the most significant bit of the output. It should be a 1. The question is, what about the overflow flag? The question now is the sign making any sense? If I subtract a non-negative number from a non-negative number, can the result be negative? Okay, so being negative makes sense. Okay, it's okay, not a problem. So in this case, the overflow flag should be a 0 because it does make sense. All right, show me one example where the sign of the result does not make any sense. Let's try 3 minus -5. Okay, actually that one still makes sense. Let's try -6. Okay, so 3 minus -6 is supposed to be positive 9. Actually, the other one would also fail too, but this one will fail as well. Okay, so let's see what we are doing here in binary. 3 is still 0011. -6 is 1010. Okay, so let's double check and make sure that is the case. Actually, I take it back. It's not 1010. -6 is 1000 is -8. 1001 is -7. So 1010 is -6. It is correct. Okay, but we can always double check. So what we want to do to find out what is the binary representation of -6 is to say, let's take the 2's complement of 6. Because 2's complement is the same thing as arithmetic negation, so that would give us the representation of -6. But 6 is not a binary number, so we have to convert it into a 4-bit binary number first. 6 is 0110, and that is the 1's complement of the same thing plus 1. 1's complement means we flip all the bits. Everything that is a 1 becomes a 0, and all the zeros become a 1. So this becomes 1001 in binary plus 1, and 1001 plus 1 is 1010. So I just double checked and make sure that the representation of -6 with 4 bits is in fact 1010. Okay, so now we are ready to actually carry out the subtraction. So let's go ahead and do that part here. So we are just going to carry out the subtraction, and This row specifies all the carries from the previous digit. So now we are ready to actually go through the computation. 1 minus 0 is a 1. 1 minus 0 is a 1. And neither gives me any borrow, so this borrow becomes a 0. 1 minus 1 is a 0. 0 minus 0 is a 0. And neither subtraction gives me a borrow, so this borrow once again is a 0. 0 minus 0 is a 0. 0 minus 0 is a 0. There's no borrow, so this one becomes a 0. 0 minus 1 is a 1, and it has a borrow. I put it here. 1 minus 0 is a 1. So the result is 1, 0, 0, 1. But the more important question is, if I'm subtracting a negative number from a positive number or non-negative number, does it make sense that the sign is negative? Let me ask that question again. I start off with a non-negative number. I am subtracting a negative number from the non-negative number. Can the result be negative? Cannot be, right? Doesn't make any sense. But yet, in this case, it is. Okay, I'm not even looking at the value. I'm just looking at the sign of the result, and it does not make sense already. So that means in this particular case, the overflow flag should be a 1. So looking at this pattern here, in general, how can we come up with an equation for the overflow flag? Well, in this case, if the first number to be subtracted from is non-negative, and we are subtracting a negative number from it, and we end up with a negative value, the sign does not make any sense, and therefore the overflow flag should be a 1. So how do we express that here? In other words, in general, if I say that we are subtracting A, whatever, 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 we are subtracting B, whatever, whatever, whatever from A, whatever, 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 and the result is C, whatever, whatever, whatever. So knowing these 3 bits as one, A, B, and C, how can we come up with an expression for the overflow flag? Okay, not A, and B, and C. That covers the first case, right? It covers the case where A is 0, B is 1, and C is 1. But there's one other case where the sign would not make any sense, and it's the exact opposite of all this stuff here. When we are subtracting a non-negative value from a negative value, and then the result somehow end up to be non-negative, that also does not make sense. Is that okay so far with the second case, which we haven't really talked about? Okay, so let me just kind of go through the second part of the disjunction here. A means the number that we are subtracting from is negative. Not B means the value that we are subtracting from that number is non-negative. Not C, oh, this is supposed to be not C, means the difference or the result of the subtraction is non-negative. Okay, sorry about that. But in this case, the sign also does not make sense. Okay, let me just give you one example to illustrate this one. So we start off with a negative number. So let's say we start off with -6, okay, which is 1010. We did that earlier. And let's say we subtract a non-negative value from it. Let's say 0011. We're subtracting 3 from -6. On this side, I would use the actual base 10 representation. So we are dealing with -6 minus 3. So in base 10 calculation, what is the result of -6 minus 3? It'll be negative 9. Okay? All right, so let's do it in binary. So when you do it in binary, I usually use one extra row for all the carry bits, or in this case, the borrow bits. And then we go through all the same rules, for the half subtractors. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 1 minus 1 is a 0. So the result, I don't even care about the other 3 bits, but the sign of the result is non-negative. So right away, I know it doesn't make any sense because the sign is wrong already. If I'm subtracting a non-negative value from a negative value, the result should be negative, and yet I'm getting a non-negative value. Overflow flag should be set. So in this particular case, A is a 1, okay? B is a 0, so not B is a 1. C is a 0, so not C is a 1. So now we have 1 and 1 and 1, which is 1. Now with a conjunction, if one side of a, if with a disjunction or, if one side is a 1 already, then the entire thing is 1, and therefore the overflow flag is also a 1 in this case. So are we doing okay so far with the derivation of the logical equation for the overflow flag in the context of subtraction? That part okay? So now we're going to take this and go back to LogicSim and modify these two guys to reflect what we just talked about. And yeah, okay. Okay, so if you look at the first gate here, the first gate at this point is negating the first and the second input. The first input comes from the first number, the second input comes from the second number. So we can modify this so that we are now subtracting a non-negative value from a negative value. So if we're subtracting a non-negative value from a negative value and the result is non-negative, then the sign does not make sense. So this gate here is now taking care of the first case. Only the first input is negated, the other 2 bits are not negated. Now we can go ahead and take care of the other one, where the first input is not negated, but the other 2 gates are negated. So we'll take a look at this one here. It got the last one negated already, or the output of the subtraction is already negated. So we just have to add negation to this one here. And now is a good time to test whether it works or not. Well, let's start with the one that is already here. 1 minus 1 is 0. Should it be overflowing? Nope. Okay, that's good. 1 minus 0 is a 1. Should we be overflowing? Nope. How about 0 minus 1? Should it be overflowing? Nope. It should not be overflowing because we are subtracting a non-negative value from a non-negative value. The result can be negative or non-negative. It really, it can be either one, and overflow should not be set in either case. Now it does give you a borrow, okay? But the borrow makes sense because we are just following the rules of subtraction in that case. Okay, so let's try to give it the 2 cases where there was a overflow situation. The first case where there was a overflowing situation is when we are subtracting -6 from 3. So let's go ahead and give that a try first. So the first number is a 1, 1, which is 3, and then the second number is -6, which is 0, 1, 0, 1. Excuse me, I take it back. 1, 0, 1, 0. So in this case, subtracting 1, 0, 1, 0, which is representing -6 from 3, gives us a overflow of 1. That makes sense. Okay, let's double check the other part. Is the sum 1, 0, 0, 1 and the carry flag is a 1? Let's go back to our text editor and see if we came up with the same result. Yep, 1, 0, 0, 1 is the result, and the carry flag or the overflow flag, the carry flag or the borrow flag is a 1 in that case. So we did all the calculations correctly, and the simulator is reflecting that. Let's try the other case where we can end up with an overflow situation by reversing these two. So this time we are subtracting 3 from negative 6. So when you subtract 3, which is 0, 0, 1, 1, from negative 6, which is 1, 0, 1, 0, once again we have an overflow here. It is non-zero, okay, the result is non-zero. The actual result is 0, 1, 1, 1, and we do not have a borrow. So let's go back to the text editor and check that is actually consistent. Everything is consistent with our calculation. The result is 0, 1, 1, 1. The result is 0, 1, 1, 1 here. It does not end up with an overall borrow, so there's no overall borrow here. The sign flag is a 0. The sign flag is a 0 here, and the overflow is a 1, just like the way we calculated it. So are there any questions about how the bits are computed from a subtraction? And subtraction is the same thing as a comparison. The only difference is what we do with the result. With a subtraction, these bits eventually will be stored back into the second operand. With a comparison, these bits are just lost. Okay, we don't care about the actual difference. We only care about the bits, the other flags that is set. So the C flag, the S flag, the Z flag, and the O flag, those will be kept after a comparison, but the actual result of the subtraction is gone. Are there any questions about all that stuff? No questions? Okay, so if there are no questions about that, then we can now focus on the concept of comparing, okay? Because comparing is one of the most important things as far as low-level programming is concerned. That is the source of most of the decision making. In other words, I'm comparing a number to the other number. If it is less than, greater than, equal to, or less than or equal to, or whatever, then we get out of the loop. So it is a control mechanism for you to stay in the loop or get out of a loop, okay, in the very simplest sense. So that's why comparison is actually very important to us. It's more important in many ways than addition or even subtraction. Okay, so let's go through some of the subtraction here or comparison here, and we want to find out is the result, is it greater than, less than, or equal to, and so on, and how would the flags be able to tell us the result of the comparison. So what we'll do is we'll start with, now in this case, signed versus unsigned makes a lot of difference. So you have to indicate whether we are dealing with signed numbers or whether we are dealing with unsigned numbers, because the way you interpret the flags is different. Even though the subtraction is done exactly the same way, the flags are set exactly the same way, you pay attention to different flags depending on whether it is signed or unsigned. Okay? So we'll go ahead and start with some examples where the result is different. Okay? When you treat a number as a signed number and when you treat the same bit pattern as an unsigned number, the result should be different. So we are always dealing with only 4-bit numbers when we're doing everything by hand, because we also have a simulator that can do it by that is also 4-bit wide. So let's first deal with a signed comparison, and you guys can tell me how -3 relates to, say, -4. Let's pick 2 here. Okay, -3 versus 2. How do they relate? Other than they're not the same. 2 is greater than -3. Okay, very good. What is the bit pattern representing -3? Now there's a quick way to do it, because 1, 1, 1, 1 is representing -1, 1, 1, 1, 0 is representing -2. So if you subtract 1 from this, it becomes -3. What is -3? 1. You're subtracting 1 from here, so it becomes 1, 1, 0, 1. Okay? 1, 1, 0, 1 represents -3 as a 4-bit number. Now you can also do it the other way around, which is the 2's complement of 0, 0, 1, 1. That is the complement, the 1's complement of the same bit pattern plus 1, which is 1, 1, 0, 0 plus 1, which is 1, 1, 0, 1. So you can do it either way. You can either do the counting thing, if it's really close to -1, or you can do the entire, two's complement computation when it's like a somewhat more of a random bit pattern. But either case, it gives us 0, take it back, 1, 1, 0, 1 is representing -3. So now we will use 1, 1, 0, 1 as a binary representation and say that is considered to be greater than 0, 0, 1, 0, because that's the binary representation of 2. Okay, that's good. In the unsigned interpretation, this time I want to take a look at 13. Okay, so we want to look at 13 and 2. How do they relate other than they are not the same? Oops, take it back. Sorry about that.
If you subtract them, they're one from the other, you're not going to get 0.
Well, it's not the same, okay? So, but other than they're not the same, how do they relate in terms of greater than or less than? 13 is greater than 2. Okay, very good. So now we are saying 1, 1, 0, 1 is greater than 0, 0, 1, 0. Because guess what? Using a 4-bit representation in an unsigned way, 13 is represented as 1, 1, 0, 1. What about in the actual computation? Okay, let's throw these bits into our trusty logic sim and find out what happens, what flags are set and what flags are reset cleared. Okay, so we are now subtracting. Now, when you're comparing, you can do the subtraction either way. So, but in most cases, we want to take the one on the left-hand side as the number to be subtracted, and then the one on the right-hand side to be the one that is subtracting the other one. So in this case, we want 1, 1, 0, 1 to be up here, and we want 2 to be down here. Okay, so we'll go ahead and take a look at this particular situation. So we have 1, 1, 0, 1, and this is 1, 0 here. Okay. These bits are not telling us the result of the comparison right away, because whether you are subtracting signed or unsigned numbers, it's using exactly the same circuitry in the processor. It's the same subtract instruction, it's the same circuitry inside the processor, using exactly the same gates to do the subtraction. So after you do the subtraction or the comparison, how do you know which one is larger when there's no differentiation between 13 and -3? They're both represented as 1, 1, 0, 1. Okay, so that's the big question. Because in C and C++, the type is associated with the value. But in assembly language programming, that is not the case. The type, or how you interpret it, has nothing to do with what bit pattern you're using, because they can boil down to exactly the same bit pattern. What you need to do is to pay attention to the flags. Which flag should I pay attention to when I look at these numbers as unsigned, and which flag should I pay attention to when I look at these numbers as signed numbers? That is the question. Okay, so when we look at these as unsigned numbers, 1, 1, 0, 1 is considered to be greater than 0, 0, 1, 0. And what you want to do in this case with unsigned is you pay attention to the carry flag. If the carry flag is set, it means the first number, whatever is on the left-hand side, is less than the number on the right-hand side. You don't pay attention to anything else. The sign flag is meaningless to you because it is an unsigned interpretation. The overflow flag is meaningless to you because it is not a signed interpretation. So anything that makes use of the sign flags is useless to you. Okay? The Z flag is useful in either case because the Z flag just tells you, are they the same? Well, whether it's signed or not doesn't matter, because if they are the same, they are the same, whether they are signed or not. Okay, so that's an easy one. Okay, for unsigned comparison, you take a look at the carry flag. If the first number or the left-hand side number is less than the right-hand number, then the sign flag is set. So I'll just kind of write it out this way. X is less than Y implies is equivalent to. Okay, so this is a much stronger statement than just implies. because it goes either way. Okay, if the carry flag is a 1 after a subtraction, it means x is less than y. And the subtraction, remember, the subtraction is x minus y. So I'll make it very clear. The carry flag is a 1 after you compute x minus y. Whether you store the result or not does not matter. Okay, the flags are affected exactly the same way. Okay, so unsigned numbers are very easy. Take a look at the borrow flag, and you have the result already spelled out for you. Okay, what about signed numbers? Well, signed numbers are a little bit more insidious. In this particular comparison, let's record the flags that are set, how the flags are set or cleared in this case. Overflow is cleared, the sign flag is set. Okay, so overflow is cleared, the sign flag is set. The Z flag is not important because as long as they're not the same, the Z flag is going to be a 0. So that's not really that important. Let's take a look at another comparison that is also a less than from the signed perspective. Okay. So give me another case where we have a less than relationship. Just pick any two numbers that can be represented in can be represented in 4 bits.
5 and 1.
5 and 1. Okay, so if you use 5 and 1, 1 would go on this side, and 5 would go on to the other side. Okay, so we want to do the subtraction and find out what flags are going to be set, which flags are going to be cleared. Do you guys want me to do it by hand, or do you want to use a logic sim to do it? Do you trust me?
I trust.
Or do you want me to show you how to do it like step by step? Or do you want to do it quick in the logic sim? Step by step? Okay, we'll do it step by step. Okay, so if we're doing this step by step, remember we are subtracting the right hand side from the left hand side. Okay, because which side is subtracted from which other side is significant. So 1 is 0, 0, 0, 1, 5 is 0, 1, 0, 1. But in base 10, we have 1 minus 5 here. So the other side, this part is just just reminding us what we are dealing with here. Okay. So this is a row that I will fill in later. But in base 10, we have negative 6 here. Okay. So we have negative 6 in base 10. And over here we have another row for all the borrow bits to get to our result. So I'm always doing these calculations in half subtractors. 1 minus 1 is a 0. 0 minus 0 is a 0. No borrow from either one. 0 minus 0, yep.
Are they both negative? The 1 minus 5?
They're not negative. Neither is negative.
And your answer should be negative 4, not negative 6.
1 minus 5 is, negative 4, that's right. Sorry for that. Okay, 0 minus 0 is a 0. See, I can do binary subtraction, but I cannot do it in base 10. It's occupational. It's an occupational kind of thing. 0 minus 0 is a 0, and neither gives me a borrow, so this borrow becomes a 0. 0 minus 1 is a 1. That gives me a borrow. 1 minus 0 is a 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with an overall borrow. Okay, so let's double check with logic sim and make sure that it comes up with exactly the same result. So we have 1 minus 5, and the result is 1100. That is 1100. We have a borrow out of the whole thing. We have a borrow out of the whole thing. The sign flag is just this flag, this bit here, so it's a 1. And the overflow flag should be what? Okay, so the overflow flag in this case is it a 0 or a 1? I'm subtracting a non-negative value from a non-negative value, end up with a non-negative value, but ends up with a negative value. Is the sign making any sense? Yeah, it makes sense. It's okay. So the overflow flag should be a 0. In logic sim, the overflow flag is also a 0. So everything is consistent. But the problem is, in this case, we have 0, 0, 0, 1 being less than 0, 1, 0, 1, and this time the overflow flag is a 0, the sign flag is a 1, and the z flag is a 0. Okay. Try something else. How about a negative number compared to a negative number? Give me two negative numbers. Either one can be -1 down to -8, and the relationship has to be less than. Okay, -7 is less than -4. So this time I'm going to be a little bit lazy and just use logic sim to do it. Now you should be able to do it by hand, but I'm just going to shortcut it and use logic sim. Okay, so -7 minus -4. What is the representation of -7? It's -8. -8 is 1 followed by all zeros. So -7, which is the next number, is just 1 followed by 2 zeros and a 1. That's the representation of -7. And then the other one is -4, which means it is okay, that's -8. That's right in the middle, right? This is -1, -2, and then we have -3, and so -4 is that. Okay. Well, let's double check. Okay, sometimes I don't trust myself. -4. So we have 0, 1, 0, 0 as 4. We want to take the 2's. They're all kind of fading already. Okay, so we are taking the 2's complement of 0, 1, 0, 0. I'm giving up on the whiteboard. All right, this is better. Okay. So we're dealing with the 2's complement of 0, 1, 0, 0, which is 4. This becomes the 1's complement of this bit pattern plus 1. So we flip all the bits, becomes 1, 0, 1, 1, and we want to add 1 to it, and that becomes 1, 1, 0, 0. So that was correct. Okay. It's always good to double check. So now we have all the subtraction done. The result is not important. The carry flag, we don't care in this case because it is a signed comparison. We don't look at the borrow flag in the signed comparison. So the only two flags that we want to take a look at is the sign flag, which in this case is a 1, and the overflow flag, which in this case is a 0. Okay, so we say in this case, we have 0, we have 1, 0, 0, 1 being considered to be less than 1, 1, 0, 0. The overflow flag is a 0, the sign flag is a 1, and the z flag is a 0. So it looks like we have a pretty general pattern here, where when the overflow flag is a 0 and the sign flag is a 1, we have the result indicated. But that's not the case. Okay, so can someone give me an example where the sign flag will be a 0 and the overflow flag will be a 1? I'll give this to you as a really quick in-class example. Can you give me the subtraction of 2-bit patterns where the overflow flag will be a 1, but the sign flag will be a 0? Now, if to overflow it means you have to be comparing the result of the subtraction has to go out of the range of what we can store in a 4-bit signed number. So give me a subtraction where the result would go out of bound.
-7 minus 3.
Sorry?
-7 minus 3.
-7 minus 3 will give us what we want. Okay, so -7 and 3. So we have -7 being less than 3. Okay, that's good. So now we want to do the computation. -7 is here already, so we just have to flip a few bits to get to 3. Okay, so we now have -7 being less than 3. But look at the bit patterns. Okay, the z flag we don't care because it is just non-zero because they're not the same number. But in this case, the sign flag is a 0, the overflow flag is a 1. Now we have somewhat of an issue because I can no longer point to one single flag and say that is what we need to look at the result and know how two signed numbers are ordered. Is that making any sense to you? That we are having somewhat of a little issue here? Oh, I forgot to. There we go. That's a sign flag. But the problem is sometimes we have the overflow flag being a 0 and the sign flag being a 1, and other times we have the overflow flag being a 1 and the sign flag being a 0. So neither is a clear-cut indicator. You cannot just look at the overflow flag and say, oh, if the overflow flag is a 1, one side is less than the other one. You cannot just look at the sign flag and say, oh, if the sign flag is a 1, this side is less than the other side. Neither one is conclusive by itself. So what you need to do, the notes actually talks about this too, is to look at both flags. If the overflow flag is different from the sign flag, then in sign interpretation, the left-hand side is less than the right-hand side. Okay, I'll say that one more time. In logic expression here. Okay, x is less than y in sign interpretation. X is less than y if and only if when you subtract y from x, it gives you the following result. It gives you the result of the overflow flag exclusive OR with the sign flag is a 1. That is what you're looking for. Okay. Okay, so we got about, well, actually we are running out of time, but I will add this part here to the logic, so we'll play with this next time. So what we're doing here is to come up with a L flag for less than, and we want to compute the L flag. The L flag is going to be based on the exclusive OR gate. So I'm going to put the exclusive OR gate here with only 2 input bits, and the other bits is 1, sorry. We want to make this narrow, only 2 inputs. One input is just the sign flag itself. The other flag is our overflow flag. The output of this, which I will put a pin next to it, and make it face west. Call that the L flag for less than. And it is a output pin. That is our less than flag. If you look at the L flag, that always indicates the correct ordering when you give 2 signed numbers for the subtractor. Okay. This is all in the notes as well. So if you read the notes, it will also talk about this. But the notes doesn't have the logic gate description, so this part is new. Okay, everything that I do in Logic Sim is not in the notes because this is the first semester that I use Logic Sim to describe the logic of how everything is actually getting done by logic gates, which I think is important. Okay, in a class like this. But everything else, is already in the notes, so you can refer to the notes for all the examples. Okay. Any questions before we end today's lecture? Yes?
When is the homework due?
The homework is due in a week. So that should be quite a bit of time, because it is in a way similar to the previous one, but in a way it is a little bit harder and a little bit easier depending on which part you're talking about. Any other questions? All right, if there are no questions, I will be in the lab in about 10 minutes.